Learning objectives. In this chapter, the user will learn the following in detail: image pyramids, sub-band coding, Haar Transform, multi-resolution expansions, discrete and continuous wavelet transforms. Introduction of wavelets. Wavelets. According to Ingrid Daubechies, if you painted a picture with sky, clouds, trees and flowers, you would use a different size brush depending on the size of the features. Wavelets are like those brushes. Wavelet transformers used to compress, transmit and analyze images. Unlike Fourier transform, whose basic functions are sinusoids, wavelet transforms are based on small waves called wavelets of varying frequency and limited duration. Small objects are viewed at high resolutions. Large objects require only a coarse resolution. The resulting wavelet image is a combination of edges, abrupt features, and homogeneous regions. Multi-resolution. The first powerful approach for signal processing and analyzing. It concerns with representation and analysis of signals at more than one solution. It incorporates and unifies the techniques including sub-band coding, signal processing, quadrature mirror filtering from digital speech recognition, and pyramid image processing. Applications of Wavelet Transform. Image compression, image transmission, image analysis. Example of wavelet analysis. An introductory example of wavelet analysis. Combination of the key features examined so far: pyramids, sub-band coding, the Haar Transform. The decomposition is called the discrete wavelet transform. With the exception of the upper left image, the histograms are very similar with values close to zero. This fact may be exploited for compression purpose. The sub-images may be used to construct coarse and fine resolution approximations. The decomposition was obtained by sub-band coding in 2D. After the generation of the 4 sub-bands, the approximation sub-band was further decomposed into 4 new sub-bands using the same filter bank. The procedure was repeated for the new approximation sub-band. This procedure characterizes the wavelet transform as the sub-images become smaller in size. This is not the Haar transform of the image. The Haar transform of the image is different. Although these filter bank coefficients were taken by the Haar transformation matrix, there is a variety of orthonormal filters that may be used. Each sub-image represents a specific band of spatial frequencies in the original image. Many of the sub-images demonstrate directional sensitivity in the upper right corner and capture the horizontal edge information in the original image. Haar Transform. It is due to Alfred Haar. Its basic functions are the simplest known. The Haar Transform is both separable and symmetric, where T equals HFH, and F is an N into N image and H is the N into N transformation matrix, and T is the N into N transformed image. Matrix H contains the Haar basic functions. The Haar basic functions Hk of Z are defined for Z lying between 0 and 1, where K equals 0, 1, n minus 1, where capital N stands for 2n. To generate H, we define the integer k equals 2p plus q minus 1, with p lying between 0 and n minus 1. If p equals 0, then q equals 0, or q equals 1. If p is not equal to 0, then q lies between 1 and 2p. For the above pairs of p and q, a value for k is determined and the Haar basic functions are computed, as shown on the screen. Example. For instance, for n equals 4, the Haar transformations will appear as shown on the screen. And for n equals 2, a similar representation is given. The rows of H2 are the simplest filters of length 2 that may be used as analysis filters. H0 of n, H1 of n of a perfect reconstruction filter band. Moreover, they can be used as scaling and wavelet vectors, defined in what follows of the simplest and oldest wavelet transform. 2D Haar Transform. Apply 1D Haar Transform to each row of the input. First and last two rows of the input are trivial. Perform averaging and differencing operation on the remaining rows. Now we can see how Haar wavelet is obtained from scaling function. Figure A shows scaling function and figure B shows the Haar wavelet function. Upper left quadrant contains average coefficients from both horizontal and vertical passes. Thus, Haar Transform is used to view original image with low noise and high frequency edge information. Upper quadrant consists of vertical averages of horizontal differences and it represents vertical edges in an original image. Same as left quadrant consists of horizontal averages of vertical differences and it represents horizontal edges in an original image. Lower quadrant consists of difference from both horizontal and vertical passes. 2D Haar Transform example. Input image of Haar Wavelet Transform. Given input image is 8x8 image. Pixel values are represented in an input image as shown on the screen. The representations of intermediate output 2D Haar Transform and output of the first level of the 2D Haar Transforms. Image pyramids. Originally devised for machine vision and image compression. It is a collection of images at decreasing resolution levels. Base level is of size 2J into 2J or N into N. Level J is of size 2J into 2J. This figure shows a simple system for creating approximation and prediction of residual pyramids. In general, a prediction residual can be defined as the difference between an image and predicted version of an image. Approximation pyramid. At each reduced resolution level, we have a filtered and downsampled image. Prediction pyramid. A prediction of each high-resolution level is obtained by upsampling, inserting zeros. The previous low-resolution, upsampling, inserting zeros. The previous low-resolution level, prediction pyramid, and interpolation, filtering. The equation for the prediction pyramid is as shown on the screen. Prediction residual pyramid. At each resolution level, the prediction error is retained along with the lowest resolution level image. The original image may be reconstructed from this information. Step 1. Compute a reduced resolution approximation of the level J input image. This is done by filtering and downsampling the filtered result by a factor of 2. Step 2. Create an estimate of the level J input image from the reduced resolution approximation generated in step 1. This is done by upsampling and filtering the generated approximation. The resulting predicting image will have the same dimensions as the level J input image. Step 3. Compute the difference between the prediction image of step 2 and input image. Place this result in level J of the prediction residual pyramid. A variety of approximation and interpolation filters are incorporated into the system. This type of filtering is performed in spatial domain. Useful approximation techniques including neighborhood averaging, which produces mean pyramids, low-pass Gaussian filtering, which produces Gaussian pyramids, and no filtering, which results in subsampling pyramids. Multi-resolution expansions, multi-resolution analysis. Image pyramids, subband coding, and the Haar transform play an important role in a mathematical framework called multi-resolution analysis, MRA. MRA scaling function is used to create a series of approximations of a signal, each differing by a factor of 2 in resolution from its nearest neighbor approximation. Additional functions called wavelets are then used to encode the difference between adjacent approximations. A signal or a function f of x may be analyzed as a linear combination of the expansion function as shown. The expansion functions are called the basic functions, and the expansion set pi of k of x is called a basis. The functions that may be expressed as a linear combination of pi of k of x form a function space called the closed span, where v equals span of pi of k of x bar. For any function space V and the corresponding expansion set, there is a set of dual function pi k of x, and it is used to compute the expansion coefficients alpha, k for any f of x summation of V as the inner product. Depending on the orthogonality of the expansion set, we have three cases for these coefficients. Case 1. The expansion functions form an orthogonal basis for V. Then the basic functions and the duals are equivalent, and the expansion coefficients are. Case 2. The expansion functions are not orthonormal, but they are an orthogonal basis for V then, and the basis and dual is called bi-orthogonal. The expansion coefficients are, and the bi-orthogonal basis and its dual are such that. Case 3. The expansion set is not a basis for V, then there is more than one set of coefficients pi k for any function of x summation V. The expansion functions and the duals are said to be overcomplete or redundant. They form a frame in which, dividing by the squared norm of the function, we see that A and B frame the normalized inner products. Case 3 continued. Equations similar to cases 1 and 2 may be used to find the expansion coefficients. Except from the normalization term, this is identical to the expression obtained for orthonormal base. Consider the set of expansion functions composed of integer translations and binary scalings of a real square integrable function pi of x as shown on the screen. Parameter k determines the position of pi of j k along the horizontal axis. Parameter j determines how broad or narrow it is along the horizontal axis. The term 2j by 2 controls the amplitude because of its shape. Pi of x is called a scaling function. By choosing the scaling function pi of x properly, the set pi jk of x can be made to span the set of all measurable square integrable functions L squared R. If we restrict j to a specific value j equals j naught, the result would be as shown on the screen. If we restrict j to a specific value j equals j naught, the resulting expansion set is a subset of that spans a subspace of L squared R as shown on the screen. That is, V j naught is a span of over 5jk of x into k as shown on the screen. More generally, as shown on the screen. Increasing j increases the size of Vj, allowing functions with fine details to be included in the subspace. This is a consequence of the fact that as j increases, the pi jk of x that are used to represent the subspace functions become narrower. Consider the unit height, unit width Haar scaling function as shown on the screen, and observe some of the expansion functions pi jk of x generated by scaling and translations of the original function. Function f of x does not belong to V0 because V0 expansion functions are too coarse to represent it. Higher resolution functions are required. Note also that pi naught of x may be decomposed as a sum of V1 expansion functions as shown on the screen. In a similar manner, any V0 expansion function may be decomposed as a sum of V1 expansion functions, again as shown. Therefore, if function x sigma V0, this is because all V0 expansion functions are contained in V1. Mathematically, we say that V0 is a subspace of V1. The simple scaling function in the preceding example obeys the 4 fundamental requirements of multi-resolution analysis, Mallet, 1989. MRA Requirement 1. The scaling function is orthogonal to its integer translates, easy to see for the Haar function, but hard to satisfy for functions which support different than 0, 1. MRA Requirement 2. The subspaces spanned by the scaling function at low scales are nested within those spanned at higher scales as shown on the screen. The fact that the Haar scaling function satisfies this requirement is not an indication that any function with the support of width 1 satisfies the condition. For instance, The simple function as shown on the screen is not a valid scale function for MRA. MRA requirement 3. The only common function to all subspaces Vj is function of x equals 0. In the coarsest possible expansion, the only representable function is a function with no information f of x equals 0. That is, the expression will take the form on the screen. MRA requirement 4. Any function may be represented with arbitrary precision. This means that in the limit, the expression assumes a form shown on screen. Under these conditions, the expansion functions of subspace Vj may be expressed as a weighted sum of the expansion functions of subspace Vj plus 1, as shown on the screen. The coefficients h pi of n are called the scaling function coefficients. This equation is fundamental to MRA and is called the refinement equation, the MRA equation or the dilation equation, as shown on the screen. The refinement equation states that the expansion functions of any subspace obtained from double resolution copies of themselves, that is, the expansion functions of the next higher resolution space. Note that the choice of reference V0 is arbitrary. We can start at any resolution level. The scaling function coefficients for the Haar function are the elements of the first row of matrix H2, that is, as shown. Thus, the refinement equation will take the form as shown. Given a scaling function that meets the MRA criteria, we can define a wavelet function psi of x that, together with its integer translates and binary scalings, spans the difference between any two adjacent scaling subspaces Vj and Vj minus 1. We define the set psi j kx of wavelets, as shown, that span the Wj spaces, as with scaling functions, as shown. The scaling and wavelet function subspaces are related by the expression as shown, where the symbol delta denotes the union of spaces. The orthogonal complement Vj and Vj plus 1 is Wj, and all members of Vj are orthogonal to the members of Wj, as shown. We can now express the space of all measurable square integrable functions as shown on the screen. This eliminates the scaling function and uses only wavelet function, again as shown. This expression contains an approximation using scaling functions V0 and wavelets from W would encode the difference between this approximation and actual functions. Any wavelet function, like its scaling function counterpart, resides in the space spanned by the next higher resolution level. Therefore, it can be expressed as a weighted sum of shifted double resolution scaling functions as shown. The coefficients h psi of n are called wavelet function coefficients. The equation can also assume the form as shown. Note the similarity with the analysis synthesis filters. The Haar scaling function coefficients were defined as shown. The corresponding wavelet coefficients are. These coefficients are the elements of the second row of the Haar transformation matrix H2. Substituting this result into as shown on the screen. We can now generate the universe of translated and scaled Haar wavelets. Any function f of x V0 may be expressed by the scaling function pi of x. Any function f of x sigma V1 may be expressed by the scaling function pi of x describing the coarse form and the wavelet function psi x describing the details that cannot be represented in V0 by pi x. Remember the function of an earlier example repeated on the screen. This indicates that it could be expanded using V0 to capture the coarse characteristics of the function and W0 to encode the details that cannot be represented by V0. The resulting expressions will take the form as shown. Sub-band coding. Another important technique with ties to multi-resolution analysis is sub-band coding. An image is decomposed to a set of band-limited components, sub-bands. The decomposition is carried by filtering and downsampling. If the filters are properly selected, the image may be reconstructed without error by filtering and upsampling. Decomposition and reconstructions are performed as digital filters in signal processing. Digital filter components. Digital filters are constructed from three main components: unit delays, multipliers, adders. A block diagram representation of a digital filter is shown on the screen. The produced filtered output sequence will be as shown on the screen. Sub-band coding. In sub-band coding, an image is decomposed into a set of band-limited components called sub-bands. The figure shows a two-band sub-band coding. A two-band filter bank for one-dimensional sub-band coding. The goal of sub-band coding is to select the analysis and synthesis filters in order to have perfect reconstruction of the signal. It may be shown that the synthesis filters should be modulated versions of the analysis filters, with one and only one synthesis filter being sign reversed of an image analysis filter. The analysis and synthesis filters should be related in one of two ways as shown on the screen. These filters are called cross-modulated. Also, the filters should be bi-orthogonal. The bi-orthogonal and orthonormal equations are shown on the screen. Of special interest in sub-band coding are filters that move beyond bi-orthogonality and require to be orthonormal. In addition, orthonormal filters satisfy conditions as shown on the screen, where the subscript means that the size of the filter should be even. Equations are shown on the screen. Synthesis filters are related by order reversal and modulation. Analysis filters are both order reversed versions of the synthesis filters. An orthonormal filter bank may be constructed around the impulse response of G0, which is called the prototype. 1D orthonormal filters may be used as 2D separable filters for sub-band image coding. A 4-band filter bank for sub-band coding comprises approximation, vertical, horizontal, and diagonal. In the diagram shown, input image is X of M, N. After 4-band filter bank for sub-band coding, we can get approximation output image A of M, N, vertical output image D power of V of M, N, and horizontal output image of D to the power of H of M, N, and diagonal output image D to the power of D of M, N. A block diagram of 4-band filtered bank for sub-band coding is represented on the screen. Example: the sub-bands may be subsequently split into smaller sub-bands. Image synthesis is obtained by reversing the procedure. The wavy lines are due to aliasing of the barely discernible window screen. Despite the aliasing, the image may be perfectly reconstructed. Time frequency analysis. The Fourier transform are shown on the screen. Time frequency transforms are shown on the screen. Heisenberg boxes. F of pi of gamma is represented in a time frequency plane by a region whose location and width depends on the time frequency spread as shown. Center mean in time domain is represented as, and the spread variance in time domain takes a form. The Plancherel formula will be center mean in frequency domain takes a form where the spread variance in frequency domain is the Heisenberg box representing an atom pi of gamma is given in figure 4. The Heisenberg uncertainty can be represented as sigma t sigma w is greater or equal to 1 by 2. Windowed Fourier transform. Window functions are real and symmetric. For a window transfer function g of t, the expressions are given on the screen. The windowed Fourier transform WFT is defined as. This is also called short-term Fourier transform STFT. Center mean in time domain. If g of t is real and symmetric, g of t is centered at 0. G mu del of t is centered at mu in time domain. Spread variance in frequency domain by Parseval theorem will appear as shown. Both of them are independent of mu and del. The Heisenberg boxes of the two windowed Fourier atoms are shown on the screen. Wavelet transformations. Continuous wavelet transform CWT, discrete wavelet transform DWT, fast wavelet transform FWT. Continuous wavelet transform. Wavelet function 0 mean will be as shown, and normalized will appear thus. Scaling by S and translating by mu, the expression takes the form. Continuous wavelet transform CWT is defined as. The wavelet admissibility condition expressions are now seen. The inverse continuous wavelet transform ICWT will be. Recall the continuous wavelet transform, which is when W function of mu, S is known for S smaller than S naught. To recover function f, we need a complement of information corresponding to W function mu, S for S smaller than S naught. Scaling function. Define that the scaling function is an aggregation of wavelets at scales larger than 1. The corresponding expressions will be. A function can therefore decompose into a low-frequency approximation and a high-frequency detail. Low-frequency approximation of f at scale S is. The inverse continuous wavelet transform can be rewritten as. Recall the continuous wavelet transform, which is. The time-frequency resolution depends on the time-frequency spread of the wavelet atoms pi mu, S. Center in time domain. Suppose that pi is centered at 0, which implies that pi is centered at mu. The spread in time domain can be expressed as. Similarly, for the equations seen on the screen, the center in time domain is mu. Spread in time domain is S squared sigma t squared. Center in frequency domain is eta by S. And spread in frequency domain is sigma w squared divided by S squared. Note that they are functions of S, but the multiplication of spread remains the same. Examples of continuous wavelets. Mexican hat wavelet, Morlet wavelet, Shannon wavelet. The Mexican hat wavelet is also called the second derivative of the Gaussian function. It takes the shape as shown. The corresponding expression for the Morlet wavelet will be. The figures on screen show the Morlet wavelet at scale 3 and its corresponding frequency spectra. The Shannon wavelet takes the form as shown on screen. Discrete wavelet transform DWT expressions follow. Let. Usually we choose n equals 2 to the power minus j. Discrete wavelet set. Discrete scaling set. Vj can be increased by increasing the value of j in the equation. There are four fundamental requirements of multi-resolution analysis MRA that scaling function and wavelet function must follow. The scaling function is orthogonal to its integer translates. The subspaces spanned by the scaling function at low resolutions are contained within those spanned at higher resolutions as shown. The only function that is common to all is any function can be represented with arbitrary precision. As the level of the expansion function approaches infinity, the expansion function space V contains all the subspaces as shown. Subspace Vj can be expressed as a weighted sum of the expansion functions of subspace. Similarly, the discrete wavelet set phi j k of x spans the difference between any two adjacent scaling subspaces Vj and Vj plus 1. The relationship between scaling and wavelet function space is shown. Any wavelet function can be expressed as a weighted sum of shifted double resolution scaling functions, as can be seen. By applying the principle of series expansion, the DWT coefficients of f of x are defined as fx can be expressed as fast wavelet transform. The fast wavelet transform is a mathematical algorithm designed to turn a waveform or signal in the time domain into a sequence of coefficients based on an orthogonal basis of small finite waves or wavelets. The transform can be easily extended to multidimensional signals such as images, where the time domain is replaced with the space domain. Computationally efficient implementation of the DWT. The relationship between the coefficients of the DWT at adjacent scales, also called Mallet's herringbone algorithm. This resembles the two-band subband coding scheme. Consider the multi-resolution refinement equation. By a scaling of x by 2 to the power of j, translation of x by k units takes the form as shown, where m equals 2k plus n. Similarly, now consider the DWT coefficient functions. Rearranging the terms, thus we can write, similarly, each bank can be downsampled for feature extraction, compression, and transmission, and then upsampled and combined for reconstruction of the original signal. The figure represents the FWT analysis filter bank. This figure represents the IFWT synthesis filter bank. By subband coding theorem, perfect reconstruction for two-band orthonormal filters requires for Gi of n equals Hj of minus n, where I equals 0, 1. That is, the synthesis and analysis filters must be time-reversed versions of one another. Since the FWT analysis filter are H0 of n equals H pi of minus n and H1 of n equals H psi of minus n, the required FWT synthesis filters are G0 of n equals H0 of minus n equals H pi of n, and G1 of n equals H1 of minus n equals H psi of n. Distinguish between wavelet transform and Fourier transform. Fourier transform. Basis function cover the entire signal range, varying in frequency only. Wavelet transform. Basis functions vary in frequency, called scale, as well as spatial extent. High-frequency basis covers a smaller area, and low-frequency basis covers a larger area. Applications of wavelet transform. Image compression, edge detection, noise removal, pattern recognition, Fingerprint verification. Conclusion. In this chapter, we have covered the following in detail: image pyramids, sub-band coding, Haar Transform, multi-resolution expansions, discrete and continuous wavelet transforms.